So in this video, I'm going to explain what my CPP code does. In previous video, I have explained how I have configured the CMake list.txt and how I have exported the CPP code as a library. Like this is the demo library, and this is how we have linked the other external libraries like OpenCV and CPP shared library like runtime. You can go and watch my previous video for that. Now I will be talking on main.cpp file what my CPP code will be doing. So there are demo library, the header file, where I have defined the functions like sum long running and solve, load image matrix, and adjust brightness. So if we are adding the CPP code, then we will be using if def C++, and this will be the line for starting and ending, and we are defining FFI plugin export to export our definitions of functions to the external environment. So main.cpp, whenever we use the CPP code, we use extern C. So first, let's start with the code. We have defined the necessary header file which will be used. This gives access to our exported function declarations. Next, a couple of macros are defined to simplify Android logcat logging, so that we can able to see the logs generated from CPP to the log Android logcat login. And there's the OpenCV to use the OpenCV SDK. OpenCV main header is included, and most namespace are inputted for like convenience, like for OpenCV and STD. The core of the code file is wrapped in extern C block. This forces C style symbol names instead of C++ mangle names, which is critical for .ffi because Dot will look up functions by their exact exported name in the share library. So I have defined a pointer to store the global original image. This acts as share native state. Like once the image is loaded via one function, another function can reuse it without reloading from disk every time. So there is the function for adjust brightness, which I will talk in later part. First, I will talk the load image matrix section. This imread caller ensures a 3-channel RGB image which matches the later assumptions for the memory layout. So before using it, the code updates the global image pointer. This ensures the cached the original image, the global pointer of image, is a deep copy of the loaded image. So even if the local image goes out of scope, later the brightness function which we'll be using can, in this top function, can still safely use the cached one. So if loading fails, we will be returning the null pointer, and we are if the image is not null, then we will set the image.rows and image.columns with this variable. And so this section, so this effectively prints a small matrix of pixel intensities to logcat, which is extremely helpful when verifying that the native load and the outside rendering agree on what the data looks like. So this is for the logging side. So there is the pointer for getting the dimensions of the image, and there is the definition to allocate a buffer for all pixels. So total pixels will be allocated for 3 channels. So image.rows into image.3, and we have used 3 channels, which is ensured by our imread caller. So we have to have that much size allocated for buffer. Again, this malloc specifically we are using it because Dot can safely call free from the same C runtime, which is a standard pattern. So there's like binders that we will be using, and we will call those free methods so that we can free the allocated memory that were allocated from here. So I will like show you how that is done. Like this is a .5, and regarding the load matrix I will show you. So there is this is the calloc.free which we are kind of calling the free function to deallocate the memory that were allocated by the CPP. So finally it walks through the image rows and columns, a channel pixel into an integer buffer, and we are per pixel will get the consecutive integers corresponding to the BGR channels, which Dot can reconstruct into an image or feed into another processing pipeline. At the end, the pointer is returned. This is the pointer returned, and Dot now has full access to the raw image data, while the CPP side keeps a cached copy for further operations like brightness adjustment. So let us see how the brightness adjustment function works in our case. So this function takes a brightness offset alpha and output parameters for rows and columns, then returns a pointer to a heap allocated in buffer. So this is a heap allocated in buffer that Dot can read. The very first thing it does is validate the global image if like available or not. So if no image was loaded, then it logs an error and return null pointer. Then it creates a new matrix and applies a brightness transformation using the convertTo with a scale of 1, and delta alpha effectively shifts all pixel values by alpha, which correspond to the image brighter or darker while keeping the same type. Next, it ensures the image really is a standard 8-bit ATU, so that's like 8-bit, and channels 3, so C3 is a channel 3. So channel 3 is ensured here, like we are reading the imread caller, which is a BGR, caller is BGR, so B one channel, G one channel, and R read another channel, so total 3 channels. So this this is important, like because the later loop assumes exactly 3 channels and bit depth, and this rows pointer and column pointer, the adjusted matrix that we have, this adjusted that the rows and columns is pointed by these pointers, and this is the buffer that we is like similar thing that we have done in the load image matrix, and we have used the malloc so that we can call the calloc in calloc.free in the Flutter bindings part. And there's another pointer which we have created for pointing to the data pointer, and we will be performing some operations here and returning that. So let me just come to the core loop. Here each vector 3v holds BGR values. Like for first time it holds the B value, V channel values, and then second iteration it holds green channel, and in the third iteration it holds red channel. And the code works like rows by rows firstly, and then column wise, and finally and write them into the contiguous BGR sequence. So finally, it returns the pointer that now owns this buffer logically and must free it using a C compatible free functions exposed via FFI. So this is the I have done in the CPP code. So I will see you in the next video how we have calling these functions using the demo library, the Dart, and how I have generated the bindings. So thank you for watching this.